What if the first definitive proof of alien technology wasn't a grand arrival, but, just a single ambiguous frame of data on a NASA live feed, visible for only a fraction of a second before the screen went black? This is the story of a hypothetical event, a thought experiment grounded in real science. On June 18th, a NASA feed tracking a fictional interstellar visitor named 3I Atlas suddenly cuts out. But not before revealing something that looks eerily artificial. Was it a simple glitch, or maybe our first glimpse of something engineered? Let's explore this together. The initial discovery. So, how does a story like this even begin? Well, it starts with the silent, relentless work of a real program, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Funded by NASA and operated by the University of Hawaii, this network of robotic telescopes with key figures like principal investigator Larry Deneau at the helm, scans the entire visible sky every 24 hours. Its primary mission is planetary defense, but its wide, fast survey is perfect for catching interstellar interlopers. In our scenario, on July 1, 2025, ATLAS flags an object on a hyperbolic trajectory. This isn't just another rock orbiting our sun. Its path proves it's a visitor from another star system, moving way too fast to be captured by our sun's gravity. After its trajectory is confirmed by the Minor Planet Center, it's designated 3Y Atlas. This would immediately trigger a global astronomical response. Scientists like Karen Meach, who led the characterization team for Oumuamua, would spearhead campaigns to observe the object with every major telescope available. This isn't just about getting a picture, it's a frantic race against time to gather data on a messenger from a distant, unknown solar system before it disappears back into the void forever. The anomalous frame. Here's the moment a routine observation becomes honestly a profound mystery. A public live feed is tracking 3I Atlas. At precisely 0317 and 12 seconds UTC, the feed freezes on a final frame before cutting to black. The image is mostly standard deep space fare, a dim, fuzzy nucleus surrounded by a cloud of gas and dust. But in the lower left quadrant, something is different. There is a razor-sharp glint of reflected sunlight forming a perfectly straight line. This is the kind of anomaly that would make a SETI pioneer like Jill Tarter take notice. Natural objects in space, comets, asteroids, dust clouds, are chaotic and irregular. Light scatters off them in diffuse, uneven patterns. But this glint is geometric. It behaves as if it's reflecting off a polished, flat surface. Independent astronomers running their own analysis software would see their edge detection algorithms flag the segment immediately. It's too consistent, too crisp. In the long search for extraterrestrial intelligence, this is exactly the type of techno-signature researchers look for, an artifact that appears manufactured, standing out starkly against the random backdrop of nature. The question is no longer just what is this comet made of, but was a part of it made at all? Data verification. An image this provocative is, well, worthless if it can't be authenticated. This is where the modern, decentralized nature of science communication becomes critical. In the minutes after the blackout, a global network of independent archivists and citizen scientists would swing into action. They run automated scripts that continuously record public NASA feeds. Packet captures of the 3I Atlas feed from servers in Germany, Australia, and the United States would be uploaded to multiple repositories. Each file, time-stamped 0317 and 12 seconds UTC, is protected by a unique cryptographic hash, a long string of characters serving as a digital fingerprint. This concept, with roots in the work of cryptographers like David Chaum, ensures data integrity. When compared, every single archived file matches, bit for bit. The German hash is identical to the Australian hash, which is identical to the original broadcast. This provides undeniable proof that the frame was not altered, manipulated, or a hoax created after the fact. The chain of custody is forensically sound, the evidence is clean. The anomaly, whatever its cause, was genuinely present in the data stream from the spacecraft. This eliminates any possibility of a simple prank and honestly forces the scientific community to confront the data as it is. Technical explanations. Before we entertain alien explanations, we have to exhaust all the mundane ones. So, why did the feed drop? The most probable official reason would be a routine network handover. NASA's deep space communications are a marvel of engineering, managed by experts like those at the Jet Propulsion Laboratory, but they aren't flawless. Signals travel from a spacecraft to a relay satellite in the Tracking and Data Relay Satellite System, or TDRS, then down to one of the 3 deep space network complexes on Earth. As the Earth rotates and satellites move, the signal must be handed off from one station or satellite to another. An engineer like Mark Raymond, known for his work on missions like Dawn, would explain that these handovers can occasionally cause a brief loss of signal. These handover blanks are common, logged, and typically last for a few seconds. They show up as a gap in the data logs with a specific reason code, so a blackout is not in itself a conspiracy. The entire system is built with these brief interruptions in mind. The deeply unsettling part of this scenario isn't the blackout itself, but its timing. A routine technical glitch occurring at the exact nanosecond a potentially paradigm-shifting anomaly appears on screen is a coincidence of astronomical proportions. Digital forensics. Let's put the frame itself under the microscope. Digital forensics is an unemotional discipline, and it offers 2 powerful non-exotic explanations for the straight edge. The first is video compression. To transmit massive amounts of data across millions of miles, images are compressed using algorithms like JPEG or MPEG. These codecs, whose development owes thanks to computer scientists like Ken Perlin for their work on procedural textures and noise, divide an image into an 8x8 pixel grid. When a faint linear feature happens to align with the grid's boundaries, the algorithm can snap it into a perfectly straight line, exaggerating its geometric appearance. It's an artifact of the math, not a feature of the object. The second culprit is a cosmic ray. Space is saturated with high-energy particles that constantly bombard camera sensors. A particle can streak across a sensor's pixels, leaving a bright, and often perfectly straight trail that lasts for only a single frame. This is a well-documented phenomenon. The most likely forensic conclusion would be a double hit. A cosmic ray created a faint streak that was then amplified and sharpened by the compression codec. It's an elegant, logical explanation that fits the evidence without rewriting any textbooks. But it can't entirely rule out that it was a real object that was simply processed by the same algorithms. 3I Atlas background. To grasp the full weight of this anomaly, we need to remember the real interstellar objects that preceded our fictional one. First came one Oumuamua in 2017. It was a complete enigma. Small, dark, and highly elongated, it showed no visible coma or outgassing, yet it accelerated away from the sun as if something were pushing it. This led Harvard astronomer Avi Loeb to famously propose it could be an artifact of extraterrestrial technology, like a solar sail. Then, in 2019 came 2I Borisov. It was a much more familiar sight, looking and behaving like a classic comet with a clear coma and tail, though its chemical composition was unlike anything from our solar system. These 2 real visitors set the stage perfectly. They proved that interstellar objects are a reality, and that they can be profoundly weird. Oumuamua, in particular, primed the scientific community to be on the lookout for anomalies. It opened the door to seriously considering technological origins. So, when 3I Atlas appears in our scenario with its own bizarre feature, it doesn't happen in a vacuum. It lands directly on the fertile ground of unresolved scientific debate and public fascination that Oumuamua left in its wake, making the stakes infinitely higher. Scientific scrutiny. In science, an extraordinary claim requires extraordinary evidence, a principle famously championed by the great astronomer Carl Sagan. A single ambiguous frame from one instrument is the very definition of not enough evidence. For the artificial edge hypothesis to be taken seriously, it would have to survive a brutal gauntlet of scientific scrutiny. First, the observation must be independently replicated. Different teams using different telescopes, like the Hubble Space Telescope or the Keck Observatory, would need to observe 3I Atlas and confirm the presence of the same geometric glint. Second, it needs to be a multi-wavelength detection. If the glint appears in visible light, does it also appear in infrared and ultraviolet? Spectral analysis of the glint itself would be crucial. If the light signature matched a known metallic alloy rather than silicate rock or water ice, the claim would gain significant credibility. As it stands in our scenario, the evidence is anecdotal. It sits on the lowest rung of the evidence ladder. Until multiple independent data streams confirm the same anomaly, the overwhelming majority of scientists would rightly remain deeply skeptical and favor a natural or instrumental explanation. The burden of proof is and must be incredibly high. 3 theories. After all the analysis, the scientific community and the public would be left grappling with 3 divergent paths. The first is the most conservative natural phenomena. A leading cometary expert, perhaps someone like Paul W. Chodas from NASA's Center for Near-Earth Object Studies, would argue that what we saw was a glint off a freshly exposed face of ice. Comets are dynamic bodies. As they heat up, jets of gas can erupt, putting immense stress on the nucleus and causing it to fracture. A large, flat piece of ice could easily shear off, and if it catches the sunlight at just the right angle, it would produce a sharp, geometric glint before tumbling away. The second path is the technical glitch theory, a perfect storm of a cosmic ray hitting the sensor in a straight line, which is then exaggerated by the video compression algorithm. It's an illusion born from the interplay of physics and software. But the third path, the one championed by thinkers like Avi Loeb, is the most profound. It posits that the object is not natural at all, that the edge is a real manufactured component of a larger object, a probe, a solar sail, or even a piece of interstellar debris from a civilization long gone. It is a long shot, but it remains a possibility that cannot be disproven with the available data. Broader implications. An event like this, even a fictional one, would transcend the world of astronomy and have profound societal implications. As Seth Shostak of the SETI Institute has often noted, the discovery of potential intelligence would change our perspective on everything. The immediate aftermath would be a firestorm of public debate about data transparency and potential cover-ups. Why did the feed cut out? Who made that decision? This would lead to intense pressure on government agencies like NASA to adopt even more radical open data policies, perhaps mandating decentralized real-time public archives for all raw telemetry. Funding priorities in science could shift overnight. Congress might allocate emergency funding to projects dedicated to the search for techno-signatures. The event also becomes a massive test of global media literacy. How does the public distinguish between credible scientific analysis and wild speculation? For a world watching, the line between healthy skepticism and unbridled wonder would blur, forcing a global conversation about our place in the cosmos and how we prepare for a discovery that could change humanity forever. One single frame could permanently alter how we look at the night sky. The search continues. While our story of 3I Atlas is a thought experiment, the real search it describes is entering a golden age. We are on the cusp of a revolution in astronomy with the imminent full operation of facilities like the Vera C. Rubin Observatory in Chile. With leading scientists like its director Zeljko Ivazic guiding the project, this observatory will conduct an unprecedented survey of the sky, discovering potentially dozens of new interstellar objects every year. This will transform the field from a data-starved science into a data-rich one. Each new visitor will be a data point, a clue from another solar system. Scientists are now actively developing the AI algorithms and observation strategies needed to characterize these objects quickly and efficiently. They are no longer just looking for comets and asteroids. They are actively hunting for anomalies. They are looking for strange light curves, unusual chemical compositions, and most importantly, objects that move in ways that defy our understanding of physics. The search is on, with more powerful tools and a more open mind than ever before. The next visitor is coming, and this time, we will be ready. The unresolved mystery of the 3I Atlas frame, though fictional, perfectly captures the tension between mundane explanation and profound possibility that drives science forward. It forces us to ask how we would react to a truly ambiguous signal from the cosmos, and highlights the absolute necessity of open data, rigorous skepticism, and relentless curiosity. What do you believe is the most compelling explanation for the anomaly and the blackout? Share your theory in the comments section below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the greatest mysteries of our universe. Thanks for watching Stellar Tech. Deep beneath Jupiter's swirling clouds, where crushing pressure should destroy any organized structure, the Juno spacecraft has discovered something that really defies the laws of planetary science. April 18, 2024, marked the day our understanding of gas giants was turned upside down, when Juno's instruments penetrated deeper than ever before and found a massive organized storm system thriving in conditions that should be, well, impossible. This terrifying discovery beneath Jupiter's surface has forced scientists to question everything they thought they knew about how giant planets work, and what secrets they're hiding in their depths. The mysterious central storm discovery. Buried beneath Jupiter's great red spot lies something that has left planetary scientists, honestly, speechless. Juno's microwave radiometer, capable of penetrating hundreds of kilometers below the visible cloud layers, revealed a massive cyclonic structure extending far deeper than any storm system should theoretically survive. Scott Bolton, Juno's principal investigator at the Southwest Research Institute, described the discovery as completely unprecedented in planetary science. The hidden storm system spans approximately 3,000 kilometers in diameter and extends at least 500 kilometers below Jupiter's ammonia cloud deck, depths where the crushing pressure should have destroyed any organized weather pattern. Unlike surface storms that dissipate when they lose energy, this deep structure appears to be feeding off Jupiter's internal heat source, creating a perpetual motion system that may have existed for centuries or even millennia. The discovery really challenges fundamental assumptions about atmospheric dynamics on gas giant planets. Traditional models predicted that Jupiter's atmosphere would become increasingly uniform with depth, but Juno's data reveals complex, organized structures persisting in regions where chaos should reign supreme. This finding suggests Jupiter's interior is far more dynamic and mysterious than anyone imagined. The beginning of the mission. August 5, 2011 marked the beginning of humanity's most ambitious journey to Jupiter, when Juno launched from Cape Canaveral, aboard an Atlas V rocket. The mission was conceived by Scott Bolton and his team to answer fundamental questions about Jupiter's formation, composition, and internal structure that had puzzled scientists for decades. Unlike previous Jupiter missions that conducted brief flybys, Juno was designed for an extended orbital campaign using a highly elliptical 53.5-day orbit that would repeatedly dive close to the planet's cloud tops. The spacecraft carried 9 sophisticated instruments, including a gravity science experiment that would map Jupiter's interior mass distribution with, honestly, unprecedented precision. Juno's journey required a complex 5-year trajectory, including a crucial Earth flyby in October 2013, to gain the velocity needed to reach Jupiter. The mission faced numerous technical challenges, including designing electronics capable of surviving Jupiter's intense radiation environment, radiation levels that would kill an unprotected human in minutes. NASA engineers had to shield Juno's sensitive instruments inside a titanium vault to prevent radiation damage during the planned 37 orbital passes around the gas giant. Jupiter is the world of chaos. Jupiter's atmosphere represents controlled chaos on a scale that just dwarfs anything found elsewhere in the solar system. Juno's JunoCam and infrared instruments revealed that Jupiter's iconic bands and zones are far more turbulent and violent than telescopic observations from Earth had suggested. Wind speeds reach 640 kilometers per hour at the equator, driven by the planet's rapid 9.9-hour rotation period that creates the fastest day of any planet in our solar system. The atmospheric bands aren't static features but dynamic rivers of gas flowing in opposite directions, creating massive shear zones where adjacent streams collide and generate enormous cyclonic storms. Candace Hansen-Koharchek, who leads JunoCam operations at the Planetary Science Institute, described Jupiter's weather as organized chaos, where small disturbances can cascade into great red spot-sized storms within weeks. The planet's atmosphere extends thousands of kilometers deep, gradually transitioning from gas to liquid hydrogen under increasing pressure and temperature. Juno's microwave radiometer detected ammonia concentrations varying dramatically with depth and latitude, suggesting complex convection patterns that transport material between atmospheric layers. This chaotic mixing prevents Jupiter from achieving thermal equilibrium, maintaining the temperature and pressure gradients that drive its perpetual storm systems across the planet's entire hemisphere. Io, the volcanic moon. Io, Jupiter's innermost large moon, represents the most volcanically active world in the solar system, with over 400 active volcanoes spewing sulfur compounds hundreds of kilometers into space. Juno's extended mission has provided, honestly, just unprecedented views of Io's volcanic activity, revealing eruptions that, really dwarf anything on Earth. The moon's extreme volcanism results from tidal heating caused by Jupiter's immense gravitational pull and orbital resonances with Europa and Ganymede. As Io orbits Jupiter every 1.77 days, these gravitational forces flex and stretch the moon's interior, generating enough heat to keep its core molten despite its small size. Alessandro Mura, from Italy's National Institute for Astrophysics, used Juno's infrared spectrometer to track individual volcanic plumes, and discovered that some eruptions reach temperatures exceeding 1,800 degrees Celsius, hot enough to melt rock instantaneously. The volcanic activity continuously resurfaces Io, making it the youngest-looking world in the solar system with no impact craters visible on its sulfur-painted surface. Io's volcanism also feeds Jupiter's radiation belts, creating a plasma torus of charged particles that contributes to the planet's deadly radiation environment that threatens any spacecraft venturing too close. Research on Jupiter's magnetic field. Jupiter possesses the most powerful magnetic field in the solar system, extending millions of kilometers into space and trapping deadly radiation that would be lethal to unprotected astronauts. Juno's magnetometer, led by Jack Connerny from NASA Goddard Space Flight Center, revealed that Jupiter's magnetic field is far more complex and honestly chaotic than Earth's relatively orderly dipolar field. The magnetic field strength reaches 4.3 Gauss at Jupiter's cloud tops, 10 times stronger than Earth's field, and is generated by electrical currents flowing through the planet's metallic hydrogen core. Unlike Earth's magnetic field, which has clear north and south poles, Jupiter's field shows irregular patterns with multiple magnetic anomalies scattered across its surface. The field appears to be generated by convection in Jupiter's outer core, where liquid metallic hydrogen acts as an electrical conductor under extreme pressure and temperature conditions. Juno's measurements revealed that the magnetic field varies significantly between different regions of the planet, suggesting complex dynamics within Jupiter's deep interior. The magnetic field creates Jupiter's enormous magnetosphere, which extends beyond the orbit of Saturn and acts as a natural particle accelerator, energizing charged particles to deadly levels that pose serious radiation hazards to spacecraft and future human exploration missions. Juno mission peaks under Jupiter's surface. Juno's gravity science experiment has, really revolutionized our understanding of Jupiter's internal structure by measuring tiny variations in the spacecraft's orbital velocity as it passes over different regions of the planet. Luciano Ies, from Sapienza University of Rome, led the gravity investigation that revealed Jupiter's core is not the solid, well-defined sphere that scientists expected, but rather a fuzzy or dilute core extending halfway to the planet's surface. The core appears to be partially dissolved, mixed with surrounding metallic hydrogen, in a way that creates a gradual transition rather than a sharp boundary. This discovery suggests that Jupiter experienced a giant impact early in its formation that disrupted its original core structure. The gravity measurements also revealed that Jupiter's atmospheric bands extend 3,000 kilometers deep into the planet, much deeper than theoretical models predicted. Yohai Kaspi from the Weizmann Institute of Science used Juno's gravity data to create three-dimensional maps showing how mass is distributed within Jupiter's interior. These measurements required extraordinary precision, detecting changes in Juno's velocity as small as 0.01 millimeters per second, equivalent to measuring the speed of a growing human fingernail from millions of kilometers away. Jupiter's formation and composition. Jupiter's formation story has been, completely rewritten based on Juno's discoveries about the planet's internal structure and composition. The traditional core accretion model suggested Jupiter formed when a solid core of rock and ice grew large enough to gravitationally capture the surrounding solar nebula gas. However, Juno's detection of a dilute core suggests a more violent formation process, involving planetary collisions that disrupted the original solid core. Tristan Guillot from the Côte d'Azur Observatory actually proposed that Jupiter may have experienced multiple giant impacts during its early formation, including collisions with Earth-sized protoplanets that scattered core material throughout the interior. The planet's composition reveals it contains between 2 and 4 times more heavy elements than the Sun, indicating Jupiter formed from materials enriched in rocks and metals beyond simple gas capture. Juno's measurements show that Jupiter's atmosphere contains water vapor at concentrations of 0.25%, which is 3 times more than previously detected, suggesting the planet formed farther from the Sun, where water ice was abundant. And the discovery of ammonia and hydrogen sulfide at varying depths indicates complex chemical processes occurring within Jupiter's interior. where extreme pressure and temperature create conditions unlike anywhere else in the solar system. Jupiter as Earth's protector. Jupiter serves as our solar system's cosmic vacuum cleaner, using its immense gravitational field to capture or deflect potentially dangerous asteroids and comets that might otherwise threaten Earth. With a mass 318 times greater than Earth's, Jupiter's gravity dominates the outer solar system and has fundamentally shaped the architecture of our planetary neighborhood. Kevin Grazier, a planetary scientist who has studied Jupiter's protective role, estimates that Jupiter reduces the impact rate of long-period comets on Earth by a factor of 1,000. The planet's gravitational influence created the Kirkwood gaps in the asteroid belt, regions where asteroids just can't maintain stable orbits due to resonances with Jupiter's 11.8-year orbital period. However, Jupiter's protection isn't absolute. The same gravitational forces that deflect some objects can also redirect others toward the inner solar system. The Shoemaker-Levy 9 comet impact back in 1994 really demonstrated Jupiter's role as a cosmic target, absorbing impacts that might otherwise threaten terrestrial planets. Juno's extended observations have revealed how Jupiter's magnetosphere interacts with the solar wind, creating a protective bubble that helps shield the inner solar system from high-energy cosmic radiation that could affect planetary atmospheres and potentially harm life. The Great Red Spot Mystery. The Great Red Spot, Jupiter's most famous feature, has been continuously observed for over 350 years, making it the longest-lived storm system known in the solar system. Juno's close-up observations revealed that this massive anticyclone extends approximately 300 kilometers below Jupiter's cloud tops and reaches temperatures of -160 degrees Celsius at its summit. Amy Simon from NASA Goddard Space Flight Center has tracked the Great Red Spot's gradual shrinkage over the past century. The storm has decreased from 40,000 kilometers wide in the 1800s to approximately 16,000 kilometers today. Juno's microwave radiometer detected that the Great Red Spot is deeply rooted in Jupiter's atmosphere, functioning as a high-pressure system that rotates counterclockwise every 6 Earth days. The storm's iconic red coloration likely results from phosphorus compounds and other chemicals brought up from Jupiter's deeper atmospheric layers through powerful convection currents. Gerald Eichstadt, a citizen scientist working with JunoCam data, has created detailed maps showing how the Great Red Spot interacts with surrounding cloud bands and smaller storm systems. The storm's longevity results from Jupiter's lack of solid surface features or continents that would disrupt its circulation patterns, allowing it to persist indefinitely in the planet's fluid atmosphere. Jupiter's deep atmospheric layers. Beneath Jupiter's visible cloud decks lies a complex atmospheric structure that extends thousands of kilometers into the planet's interior, gradually transitioning from gas to liquid under increasing pressure. Juno's microwave radiometer has penetrated deeper into Jupiter's atmosphere than any previous instrument, revealing ammonia concentrations that vary dramatically with depth and latitude in patterns that really defy simple atmospheric models. Chung Lee from the University of California, Berkeley discovered that ammonia becomes depleted at certain depths, suggesting complex chemical processes and circulation patterns that transport materials between atmospheric layers. The atmospheric layers include distinct regions: the upper troposphere where visible clouds form, the deeper stratosphere where temperatures increase with altitude, and the thermosphere where solar radiation heats the thin gas to over 1,000 degrees Celsius. Lee Fletcher from the University of Leicester used Juno's infrared observations to map temperature variations that reveal convection cells extending hundreds of kilometers below the cloud tops. The deep atmosphere shows evidence of phosphine gas, carbon monoxide, and methane that really shouldn't exist at those depths according to chemical equilibrium models. These discoveries suggest that Jupiter's deep atmosphere is actively mixed by powerful convection currents that transport chemicals from the hot interior to the cold upper atmosphere, creating a dynamic system that continues to challenge our understanding of giant planet atmospheric dynamics. Juno's deep scan of Jupiter has revealed a world far more complex and mysterious than anyone imagined. From the dilute core that defies formation theories to the organized storm systems lurking beneath the clouds, Jupiter continues surprising scientists with each new discovery. The gas giant's protective role in our solar system and its extreme atmospheric dynamics make it both fascinating and honestly, kind of terrifying. These revelations prove that even after centuries of observation, Jupiter still holds secrets that could reshape our understanding of planetary science. Subscribe to Stellar Tech for more incredible discoveries from the frontiers of space exploration. What if the most profound discovery in human history was made, and then deliberately buried? We're not talking about rumors or grainy photos here. We're talking about 24 gigabytes of classified NASA data on an interstellar visitor that, well, defied the laws of physics. Data leaked by a ghost-like hacker group revealing a 26-kilometer-wide object that wasn't just passing through our solar system but was actually, actively navigating it. This is the story of 3I Atlas, what NASA allegedly found and why they never wanted you to see it. Let's delve into the data. Event Horizon cyber attack. So how does a clandestine group get its hands on NASA's crown jewels? According to the leaked security logs, this wasn't a brute force attack, it was surgical. In the early hours of September 2, 2025, Event Horizon executed a coordinated cyber attack that bypassed multiple layers of agency firewalls. They exploited a zero-day vulnerability in an outdated Fortran-based mission planning module, a tiny crack in an otherwise formidable digital fortress. The transfer rate was a blistering 571 megabits per second, far too fast for automated security flags to catch in time. Forensic analysts later pieced together a chilling timeline. The attackers gained initial access at 3:14 a.m. Eastern, escalated their privileges to the highest level by 3:19, and began siphoning data at 3:23. In under 7 minutes, 24 gigabytes of compressed files, including internal chat logs, draft reports, and sensitive telemetry from the 3I Atlas intercept mission, were gone. By 3:30 a.m., the connection vanished, leaving behind nothing but a silent gap in the audit trail. Cybersecurity expert Mikko Kaku has stated that such an attack would require nation-state level resources, suggesting Event Horizon is far more sophisticated than a typical hacktivist group. The manifesto and distribution. A data breach is one thing, but a declaration of war on secrecy is another. Within hours of the hack, a manifesto from Event Horizon appeared on encrypted forums. Their message wasn't a boast, it was a justification. They claimed the breach was a direct response to what they termed unlawful cosmic secrecy, arguing that discoveries of this magnitude belong to humanity, not to a select few government agencies. The manifesto warned that the stolen files contained information so sensitive even senior directors at NASA were allegedly unaware of its full scope. Their language was direct: the world deserves to know what its own scientists have found. To prove their point, they began a strategic distribution campaign. Blurred screenshots and heavily redacted memos were sent to journalists and channels known for covering classified science. They specifically avoided mainstream outlets, opting for platforms that would analyze the data without an institutional filter. This drip feed of information created a groundswell of speculation that legacy media couldn't ignore, forcing the conversation into the open on Event Horizon's terms. Authenticating the documents. In the world of leaks, authenticity is paramount, so are these files real? The evidence presented by Event Horizon is compellingly layered. The leaked screenshots are plastered with authentic details: bold, block-lettered confidential stamps, thick redaction blocks, and metadata tags showing UTC timestamps that perfectly match the breach window from NASA's own security audit. We see mission patch artwork in the corners, a stylized comet labeled 3I Atlas Int. Every document carries unique identifiers, routing codes, and internal chat handles you'd expect to see inside a major agency. Technical diagrams and draft tables use Courier font headers and bear NASA's internal digital watermark. We even see screenshots of the classic blue and white NASA email interface, with subject lines like Atlas Intercept Immediate Action Required, and Telemetry Review Anomaly Detected. One partially blurred memo lists technical trajectory data, while another redacted report is marked with the access level TSSCI, denoting top secret sensitive compartmented information, a classification that restricts access to a small, specific group of cleared individuals. The documents bear digital signature strings ending in JPL for the Jet Propulsion Laboratory, and GSFC for the Goddard Space Flight Center, indicating a multi-center collaboration. Discovery of 3I Atlas. Before the leak, there was the discovery that started it all. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS survey in Hawaii, logged a new object tearing into the solar system at 130,000 miles per hour. Astronomers flagged it immediately. This was no ordinary comet. The object, soon labeled 3Y Atlas, measured an estimated 26 kilometers across, roughly the size of Manhattan, moving faster than any object ever observed inside the orbit of Jupiter. Veteran survey scientist Dr. Lina Takahashi, a fictional name from the leaked files, was quoted in a log. The track was so steep, the software flagged it as an error. Within hours, observatories from Chile to Arizona confirmed the numbers. The object's incoming speed of over 58 kilometers per second defied the sun's gravitational grip. Its trajectory pointed back toward the constellation Lyra, far from the ecliptic plane where most solar system debris resides. To put its size in perspective, the asteroid that killed the dinosaurs was only about 10 kilometers wide. This was over twice that, and it wasn't from around here. Impossible physics and trajectory. Here's where the story takes a sharp turn from unusual to unbelievable. Like its predecessor Oumuamua, 3I Atlas was not behaving according to the laws of physics. The leaked mission logs from July 18, 2025, show a sudden, inexplicable sideways acceleration resulting in a velocity change, or delta V, of 1.5 meters per second. The object changed course in a way that defied gravitational models. For a normal comet, such a deviation could be explained by outgassing, measured by the non-gravitational acceleration parameter, A2. However, just like with Oumuamua, initial observations of 3I Atlas showed no cometary tail, no dust, and no gas coma to account for the push. Its A2 parameter was effectively zero, yet it was still maneuvering. Trajectory analysts were stumped. They ran models accounting for solar radiation pressure, gravitational pulls from planets, and every known natural force. Nothing matched the telemetry. Dr. Amy Mainzer, a leading expert on asteroids, has noted that explaining such a deviation without observable outgassing requires exotic physics or an artificial origin. The numbers kept pointing to a single, unsettling conclusion. Some force other than gravity was steering this massive object through our solar system. Surface anomalies, the armor problem. What does a 26-kilometer object from another star system look like? The first leaked images from the Intercept mission were paradigm-shattering. 3I Atlas's surface resembled no comet on file. Imaging analysts flagged a pattern of smooth, almost metallic-looking plating, broken by lines that ran too straight to be natural fractures. One analyst, quoted in a redacted chat log, called it the radiator problem, referring to a gridwork of raised ridges spaced like the cooling fins on spacecraft. These ribs cast long, uniform shadows, and their regularity caused the anomaly detection software to flag the pattern as artificial. Comparisons to known comets like Halley or 67P Churyumov-Gerasimenko fell apart. Their surfaces are jagged and chaotic. 3I Atlas, in contrast, had long stretches that reflected sunlight like polished alloy. Further spectral analysis of this reflected light showed an albedo inconsistent with any known meteoritic iron, lacking the usual chondritic features. It was too smooth, too reflective, and far too structured. Thermal signatures and heat pulses. If the surface looked engineered, the thermal data was even more alarming. According to the leaked files, infrared arrays recorded heat vents pulsing with incredible regularity. The logs show heat pooling along the strange ribbed seams and then bursting outward in tight, directed jets. This wasn't the broad, chaotic outgassing you see in a typical comet. These were discrete, timed pulses occurring precisely every 90 seconds, raising local surface temperatures by over 200 degrees Kelvin in an instant. The mission logs classified this as a directive motion event, a term typically reserved for spacecraft thrusters, not natural phenomena. Even more damning, trajectory analysts correlated these thermal pulses directly with the object's mysterious course corrections. After each 90-second heat burst, the Intercept team logged a subtle but precise shift in its path. The efficiency of this propulsion, measured as specific impulse, was calculated to be far beyond any chemical rocket, consistent with advanced ion or plasma thrusters. Gravity couldn't explain it, solar radiation is constant, and natural outgassing is random. The evidence was building 3I Atlas wasn't just moving strangely, it appeared to be actively propelling itself. Chemical composition mysteries. The mystery only deepens when you look at what 3I Atlas was made of. Martin Cordner's team at Goddard was the first to get a full spectrum after the Intercept, and the results were an instant red flag. The early spectra lit up with incredibly sharp, bright lines of nickel. In cosmic bodies, nickel almost always rides shotgun with iron. Yet in every single frame of data from 3I Atlas, iron was almost completely absent. Its signature spectral lines were missing. This isn't just rare. In the entire catalog of known comets and asteroids, it's unheard of. The natural formation processes that create asteroids from protoplanetary disks simply don't separate these two elements with such purity. Leaked notes suggest the isotopic ratio of the nickel was also wrong, indicating it wasn't formed in a typical supernova. The purity level was estimated to be over 99.8%, a level that on Earth requires an advanced electrochemical process known as the Mond process. Radio echoes and communication patterns. Beyond its motion and materials, the most chilling evidence in the leaked files points toward active technology. According to the logs, radio astronomers reviewing raw data from the Intercept mission flagged a pattern of faint, repeating echoes in the X-band frequency range. These weren't natural radio bursts or cosmic static, they were precise, clipped signals with a high signal-to-noise ratio, bouncing back from 3I Atlas at regular intervals. What made this truly shocking was the timing. The interval of the radio echoes mapped almost perfectly to the 90-second rhythm of the object's thermal pulses. It was as if something was pinging the object, and the heat pulses were the response. In one of the leaked chat logs, a veteran telemetry specialist reportedly wrote, "It's like someone is pinging the probe and it's answering. The pattern is too tight for random noise." This completely changed the nature of the investigation. SETI pioneer Dr. Jill Tarter has long argued that a truly intelligent signal would likely be efficient and information-dense, characteristics that align with these alleged repeating echoes. The data suggested it could be an active, responsive probe. Expert analysis and propulsion theory. You can't discuss these anomalies without bringing in a voice of scientific courage like Avi Loeb. The Harvard astrophysicist, who famously staked his reputation on Oumuamua being alien technology, wasted no time weighing in on the 3I Atlas files. He argued the intercepted telemetry read like a blueprint for an advanced propulsion system. Each 90-second heat pulse and corresponding course correction was perfectly consistent with a massive ion drive or a similar engine. In Loeb's words, if you wanted to navigate through a solar system while managing heat and energy, you would use timed, directional thrust. That is what the data shows. But the most jarring evidence was a fragment recovered by the interceptor's dust collector. A leaked lab memo described a fleck of material with a lattice of silicon and doped phosphorus, arranged in layers spaced at micron intervals. The structure was noted as being radiation-hardened to a degree far beyond current human capability, suggesting it was built for long-duration travel through the harsh interstellar medium. This wasn't just a circuit, it was an artifact from a civilization far beyond our own. So what do we make of all this? A 26-kilometer object from another star system, moving at impossible speeds, making its own course corrections. It has a surface that looks like armor, a composition of refined nickel, and it pulses with heat and radio echoes on a perfect 90-second clock. And finally, there's a fragment of what appears to be a microchip. The leaked files, if authentic, present a disturbing and profound reality. The questions are staggering. What is this object's purpose? Where did it come from? And perhaps most importantly, what else has NASA found that we don't know about? Don't forget to like, subscribe, and hit the bell icon for more deep dives into the secrets of science and technology. Thanks for watching Stellar Tech. A rare visitor from deep space is flying through our solar system. The object, now officially named 3I Atlas, has astronomers spotting another mysterious interstellar visitor racing through space. NASA's recent data has revealed anomalous features that have sparked intense debate over its true nature. Some scientists fear the possibilities this mysterious visitor presents, suggesting it could be more than a mere comet or asteroid, perhaps even a disguised alien ship. This revelation has generated both excitement and apprehension within the scientific community as we strive to understand its origin and purpose. The breaking discovery. The initial detection of 3I Atlas occurred in early 2025 by the Atlas Survey System, an automated telescope array designed to spot near-Earth and interstellar objects. Astronomers were immediately intrigued by the object's extraordinary velocity and hyperbolic trajectory that clearly indicated it was not gravitationally bound to our solar system. Dr. Larry Deneau, lead scientist for the Atlas project, confirmed the object's unique path and immediately alerted observatories worldwide to begin tracking this unprecedented visitor. The breaking revelation that 3I Atlas was significantly larger and faster than previous interstellar objects reignited debates about the prevalence of such cosmic travelers. The discovery highlighted the increasing sensitivity of modern astronomical detection tools and emphasized the critical importance of global coordination in tracking these extraordinarily rare cosmic interlopers. Initial observations revealed unusual characteristics that defied conventional explanations for natural interstellar objects. The object's behavior patterns suggested it might possess properties unlike anything previously encountered in our solar system. This discovery marked a pivotal moment in interstellar object research, forcing scientists to reconsider fundamental assumptions about what travels through the void between stars. The discovery story. Following the initial detection, astronomers rapidly organized international efforts to gather comprehensive observational data on 3I Atlas during its brief passage through our solar system. Utilizing powerful instruments including the Hubble Space Telescope and sophisticated ground-based observatories, they systematically confirmed the object's size, composition, and increasingly unusual behavioral characteristics. The European Southern Observatory contributed crucial spectral data revealing complex surface features that appeared inconsistent with known cometary or asteroidal bodies. Dr. Michelle Bannister from the University of Canterbury discussed the significant challenges involved in imaging such a fast-moving, distant object while maintaining the precision required for detailed analysis. The collaborative international effort underscored both the urgency and scientific significance of capturing comprehensive models of 3I Atlas during its fleeting passage through our cosmic neighborhood. Teams worked around the clock to coordinate observations across multiple time zones and hemispheres. The unprecedented level of cooperation demonstrated the scientific community's recognition that this visitor represented something truly extraordinary. Each new observation added pieces to a puzzle that seemed to defy conventional understanding of interstellar objects and their expected properties. A stranger in our midst. 3I Atlas exhibits characteristics unlike any object previously observed in our solar system or beyond. Recent measurements indicate it possesses unusually high reflectivity and metallic surface characteristics that fundamentally defy typical comet or asteroid classifications used by astronomers. Dr. Alan Fitzsimmons from Queen's University Belfast analyzed extensive telescope data, highlighting the strange spectral signatures indicative of advanced materials, rather than natural rocky or icy compositions. Traveling at nearly 60 kilometers per second, the object exhibits unexpected trajectory modifications that some researchers interpret as evidence of artificial propulsion systems. These remarkable anomalies have led a growing number of scientists to propose that 3I Atlas may represent a technological artifact, possibly an extraterrestrial probe deliberately sent to observe our planetary system. Continued observations aim to definitively determine whether its behaviors represent unknown natural phenomena or constitute evidence of intelligent design and construction. The object's surface appears remarkably smooth and uniform, lacking the typical irregular features expected from natural cosmic debris. Its thermal emissions follow patterns that suggest internal heat sources, rather than simple solar heating. These discoveries have fundamentally challenged existing models of what interstellar objects should look like and how they should behave. The predecessors. The previous two confirmed interstellar visitors, known as 1I/Oumuamua discovered back in 2017 and 2I/Borisov detected in 2019, provide crucial context for understanding 3I/Atlas. Yet, none of these objects actually share its peculiar characteristics. Oumuamua, for instance, initially baffled scientists with its really unusual cigar-like shape and that completely unexplained non-gravitational acceleration, which honestly just defied conventional physics. In stark contrast, 2I/Borisov displayed classic cometary behavior, showing typical outgassing patterns and developing a visible tail, just as you'd expect from natural objects. 3I/Atlas, though, with its massive size and highly reflective surface properties, fundamentally challenges the notion that interstellar objects always conform to previously known natural archetypes. The growing dataset from these three dramatically different visitors is systematically reshaping our understanding of what might actually be actively traversing our galaxy. Each visitor has contributed unique insights while, at the same time, raising increasingly complex questions about the diversity of objects traveling between star systems. The progression from Oumuamua's mysteries to 3I/Atlas's apparent technological signatures really suggests an escalating complexity that, well, demands serious reconsideration of our assumptions about interstellar space and its contents. The Cosmic Journey. The cosmic journey undertaken by 3I/Atlas spans potentially billions of years, originating from some unknown star system located far beyond the boundaries of our solar neighborhood. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory explains that the object's estimated age and remarkable velocity suggest it has successfully survived countless cosmic events, stellar encounters, and gravitational interactions during its extended voyage. Its calculated trajectory indicates a passage through the harsh environment of interstellar space for, wow, potentially over a billion years, making it an ancient relic from the early epochs of galactic formation. Sophisticated spacecraft instruments have detected faint emissions, possibly linked to its primordial origin, which offers researchers a unique observational window into materials and processes from beyond our solar system. Understanding this extraordinary journey provides crucial insights into the fundamental processes shaping galactic evolution and the distribution of matter throughout cosmic history. The object's apparent structural integrity after such an immense voyage raises some pretty profound questions about its composition and construction. Natural objects typically show significant degradation after extended exposure to cosmic radiation and micrometeorite bombardment, yet 3I/Atlas appears honestly remarkably well preserved. A scientific goldmine. The discovery of 3I/Atlas represents without a doubt an unprecedented scientific opportunity, with an international array of telescopes and observatories now focused on capturing every possible detail during its passage. Scientific teams from NASA, ESA, and numerous other agencies are collaborating intensively to analyze spectral data, refine orbital models, and systematically search for evidence of non-natural phenomena. Dr. Sarah Seeger from the Massachusetts Institute of Technology emphasizes the extraordinary opportunities this visitor presents for studying interstellar chemistry, exotic materials, and potential technological signatures. The comprehensive data collection effort could, potentially unlock fundamental secrets about planetary formation processes in distant star systems and provide insights into the prevalence of advanced technology beyond our solar system. Each observation is carefully coordinated and scheduled to maximize scientific return during the object's limited time within optimal viewing range. The international cooperation on this project demonstrates unprecedented levels of coordination among research institutions that are typically quite competitive. Advanced imaging techniques are revealing surface details that really challenge our conventional understanding of natural space objects. Spectroscopic analysis has detected unusual emission lines that don't match any known natural materials, fueling speculation about artificial construction and exotic engineering materials. Unanswered questions. Despite extensive international study efforts, fundamental questions about 3I/Atlas remain frustratingly unanswered, leaving scientists divided about its true nature. Dr. Avi Loeb of Harvard University points out that certain observed behaviors definitely defy all known natural processes, including, unexplained acceleration patterns and highly unusual surface reflectivity characteristics. The object's true internal composition, structural configuration, and ultimate origin remain completely elusive despite intensive investigation. Competing hypotheses range from exotic natural cometary remnants to sophisticated artificial probes, potentially sent by extraterrestrial intelligence for reconnaissance purposes. Ongoing research efforts focus intensively on resolving these mounting mysteries, bolstered by significant advances in instrumentation and increasingly sophisticated observational techniques. The international scientific community remains fundamentally divided, carefully balancing healthy skepticism with genuinely open-minded inquiry as new data continues emerging. Some researchers argue for natural explanations involving unknown physics or exotic materials, while others increasingly favor artificial origin theories. The lack of definitive answers has created intense debates within astronomy journals and conferences. Each new observation seems to deepen rather than resolve the central mystery surrounding this enigmatic visitor from interstellar space. The alien question. The possibility that 3I/Atlas represents alien technology has moved from fringe speculation to serious scientific consideration among mainstream researchers studying its anomalous properties. Evidence supporting artificial origin theories includes the object's unusual mathematical heat emission patterns, sophisticated trajectory adjustments, and surface materials that appear inconsistent with natural formation processes. Dr. Seth Shostak from the SETI Institute reports that thermal emissions follow prime number sequences that are extremely unlikely to arise naturally and may represent deliberate signals or encoded information. This finding significantly strengthens the possibility that the object functions as part of a broader network of interstellar probes, communicating through universal mathematical codes that any technological civilization would recognize. The hypothesis suggests systematic interstellar exploration conducted by advanced civilizations using sophisticated reconnaissance technology designed to remain undetected until closely observed. Understanding these potential signals could fundamentally transform our approach to searching for extraterrestrial intelligence and establish first contact protocols. The implications extend far beyond academic interest, potentially representing humanity's first confirmed encounter with technology from another world. Such a discovery would necessitate careful consideration of response protocols and international cooperation in managing potential contact scenarios. Observing the visitor. The global astronomical community has mobilized unprecedented resources to observe 3I/Atlas, coordinating space-based telescopes, ground observatories, and advanced detection systems worldwide. Dr. Nancy Grace Roman's space telescope operations have been specially configured to track the object's trajectory and capture high-resolution images during optimal viewing windows. The Vera Rubin Observatory contributes continuous monitoring capabilities, while radio telescope arrays search for potential technological emissions or communication signals. Dr. Michelle Bannister from the University of Canterbury coordinates international observation schedules to ensure maximum coverage as the object traverses different regions of sky visibility. Advanced spectroscopic analysis reveals surface features that appear artificially smooth and uniform, lacking the typical irregularities expected from natural cosmic debris shaped by millions of years of space weathering. Thermal imaging detects internal heat sources that suggest active systems rather than passive solar heating patterns typical of natural objects. The coordination represents the largest international scientific collaboration in astronomical history, with researchers sharing data in real time across continents. Each observation window provides crucial data that may determine whether humanity faces a natural phenomenon or evidence of extraterrestrial technology visiting our solar system. Dawn of a new era. The implications of 3I/Atlas extend far beyond simple astronomical curiosity, potentially marking the dawn of a new era in humanity's understanding of our cosmic environment. Dr. Michio Kaku from City College of New York suggests that whether this object proves natural or artificial, it fundamentally challenges our assumptions about life, intelligence, and technology in the universe. The systematic study of 3I/Atlas has already driven innovations in observational technology, international cooperation protocols, and theoretical frameworks for understanding interstellar phenomena. These technological and methodological advances position humanity to better detect, analyze, and potentially interact with future cosmic visitors. The growing frequency of interstellar object detections suggests we may be entering an era of regular contact with materials and possibly intelligence from beyond our solar system. Future missions may attempt direct rendezvous with similar objects to conduct detailed analysis impossible from Earth-based observations. The scientific community recognizes that 3I/Atlas represents either an extraordinary natural phenomenon or humanity's first confirmed encounter with extraterrestrial technology. Either conclusion would fundamentally alter our understanding of our place in the cosmos and our readiness to engage with a potentially populated galaxy. The ongoing study of 3I/Atlas continues to challenge everything we thought we knew about interstellar visitors and our place in the cosmic community. Whether this mysterious object represents advanced alien technology or an exotic natural phenomenon, its discovery has already transformed our approach to studying the universe around us. As observations continue and data accumulates, humanity stands at the threshold of potentially world-changing revelations. Stay with Stellar Tech for continued coverage of this developing story that may forever change our understanding of life beyond Earth.